Welcome to ETHDam, to ETHDam, to ETHDam, to ETHDam, to ETHDam.
First of all, hello to everyone. This is basically like a case study of the work we've been doing in Enigma for DeFi protocols, but wrapped in a talk in some way. So, just maybe a little bit of background. I'm Victor Martinez. I've been doing like fuzzing and blockchain security stuff for, I don't know, 3 years or 4 years already. And last year we founded Enigma Dark. Wade and I, he's here. And we do like top tier security services for protocols mostly. And one of those is fuzzing. So what exactly is fuzzing? Fuzzing is just taking a program and throwing random inputs at it while you monitor like assertions or stuff breaking into the program, right? So you have your fuzzing tool. You have the in this case the program is an Ethereum smart contract. So we have the fuzzer calling the Ethereum smart contract, and then we implement a few different checks to make sure that everything runs as expected, and that way we can start doing invariant testing using fuzzing, because invariant testing is basically just checking those invariants into like a whole lot of states. For tooling, we will go over the main tooling for fuzzing. The usual one is Foundry, is the most used one, but it's only useful for the stateless tests, I think, like so far compared to the other two tools. So for stateless tests, we have Foundry. The same way you can do, like you do a unit test in Foundry, you can do like a fast test with Foundry as well. So it's pretty straightforward. And then we have Medusa and Akina. Those are the most interesting tools because we can wrap like the behavior of the tools into a framework, into an actor-based framework to simulate everything that could happen in real life on a protocol, but locally with the tools. So we don't have to get hacked. We can prevent the bugs. So yeah, basically we use Akina and Medusa, and we always recommend to use those if you want to use the same setup and the same framework that you would, or the way of the reasoning behind it that we use. So the case study, we've been working with AAVE for the V3, Euler for the V2, Silo for the V3, and many other protocols. I just have a few here. So we will see some cases, some interesting stuff that we found, and or maybe some concerns that we were able to find with this technique, fuzzing and invariant testing. So what's an invariant suite? An invariant suite is like a suite of tests, but you have here what would be like an abstracted version of a protocol. So maybe a whole deployment of the AAVE v3 protocol, and then we have like a suite of tests. It's basically just one contract inheriting all the functionality for the suite to work. And the most important part of the suite are the actors. The actors are just like some kind of proxies for the tool. The tool uses like random addresses, like a set of predefined addresses to call the harnesses in this context. So basically this just wraps everything and lets, they act similar to smart accounts in some way. So they are smart contracts and they just interact with the protocol, and we can assert stuff, we can basically call everything on the protocol from the suite, from the harnesses, and check a lot of stuff. Also, another thing to mention regarding the difference between Foundry and Medusa and Akina is that Foundry, these tools, in order to work really good, they have something called path exploring or coverage guidance. And basically, whenever they run, each time they run at least a bit more efficient, or they are able to find like more paths into the protocol or into the system, because they just store and like learn from previous runs. So that's like a huge thing about Akina, especially Akina. We usually use Akina. So yeah, and we have like a different types of modes that we will cover later. So yeah, types of properties on the framework, on the Enigma framework, really similar to what other companies are doing, like mostly formal verification companies, because we don't like to make that many unit tests. We think that global invariance, stuff like the total balance of the protocol should be equal to the sum of the user balances. That's a global invariant, and those are the ones we tend to focus the most on, because then you can just assert the stuff like that and get to a state that breaks that invariant, and then roll back, like kind of engineer back everything or debug everything into the root cause. You don't have to go explicitly for the root cause. Then we have the global post conditions. Here we just cache values before and after the calls, and then compare. It's like asserting rules on state transitions instead of on the states directly. And then 100 specific post conditions are just some specific stuff. For example, if I have one rule for liquidations on a liquidation function, I don't want that rule to be checked on deposits or on withdrawals or stuff like that. So yeah, let's get straight into Euler. Euler for the EBK, if you are not aware of it, it's like a new super modular and super interesting lending protocol, and it's everything works like on with the EBC and with the EBK. The EBK is the framework that you can build or use it to make lending protocols yourself, but integrated with Euler, of course. Yeah, so the main invariant on lending protocols, we try to abstract everything in classes, in back classes or in areas. So one of them is the availability of the functions. We want repayment functions to always be callable, to never be in a DOS, like in a DOS state. So basically we were with this, with a suite we built for Euler, we were able to find some specific edge case, simulating all the functions on the protocol, some specific edge case that made users not able to repay debt in some case. Obviously, this is in like an early stage of the protocol. They fixed everything. The protocol is secure, but this was some edge case that we are able to find because we are using fuzzing and invariant testing. As you can see, we debugged everything back and found the root cause with the Euler team as well. Then let's go to AAVE3. For the example of AAVE3, instead of showing like a bug we found, we are going to show some of like an example of a big invariant, like a global invariant. And in this case, it'd be like the 8 token total supply. AAVE uses 8 tokens for balances. So the 8 token total supply should be equal, or at least between some deltas, to the sum of all user balances. So what we have here is we are able to, like a helper function, like an assertion function, where we are able to query the state from the protocol, from the fuzzing suite, and then assert different stuff. The tool will break if it finds, if it makes the protocol go to a state where it breaks everything, basically. So we will get the call trace back. This is another interesting step. The project, I think it's stealth, I don't know yet, but it's just mentioning some random thing or idea or heuristic we usually work to lately, and is normally when you set up a fuzzing suite, the idea is like that. You basically deploy everything, set up the oracle prices, the initial prices, I mean. So you always start from this part, and then the fuzzer starts like making random calls, deposit, withdraw, whatever, and the protocol is able to reach a different state, right? This is with the normal version of fuzzing. For some kind of protocols like AMMs and like little protocols, but with a lot of complexity on them, let's say, or parameter heavy, like parameter heavy on the deployment, we can also, instead of deploying, we can randomize the deployment. So each time we are going to start from a different point. So instead of just looking like that, like and actually go into on every path, we are actually to start from a different initial position. So we are just finding more stuff with this. I think it was pretty useful when we found this at 4 a.m. probably, like working on a protocol. And yeah, then some techniques to not use or to avoid using with fuzzing, clamping, and many other forbidden techniques. Overclamping is basically using mod math or like modulos to actually clamp values and not to lose them, because, for example, if I don't have 1,000 tokens and I try to deposit 1,000 tokens, the call will revert, the Akina will just skip to the next call. But you can do some clamping stuff that, for example, lets you deposit only the amount that you have. But then you are obviously like discarding a lot of those paths that were the interesting ones, because those are really on the stuff that people don't look into, is where the edge cases lie at. So I really recommend to not clamp, just let the coverage algorithm do the work, the path exploring algorithm do the work. Overmocking, I will show you an example now, so we can finish. Overmocking is a big pain, even on like normal tests, because people try to mock everything, like oracles, bolts, underlying bolts, even tokens, and it's not how real life works. So here, if I'm trying to actually make a program simulate the behavior of another program, in this case, a protocol, for example, I'm gonna try to make it as real as possible in some way. So then we have missing coverage, bad reports. People just run the tools, and the tools are super complicated in some way. So they don't actually check coverage. They don't check coverage, or they check different kinds of coverage, but not the right one. So missing coverage is basically the tool is not checking in that place, so you cannot actually check nothing. Hard-coded values, same for stablecoin pegged assets, Oracle prices. You should simulate everything. And then there's also like a quick note here about not using allowances. Normally, when you simulate the stuff, you should use allowances, because normally there's bugs on allowances that if you, for example, you can deposit for another user for the to address, and you are always depositing to yourself through the fuzzing suite. You are not reaching that state where I can deposit for another person, or I can borrow on behalf of another person, stuff like that. So yeah, this was just a quick example about the mocking. Say, for example, nowadays, like lending protocols are doing, like, for example, for Morphobots, for example, we have like the underlying protocol, or for many other protocols, and now they are building some kind of yield aggregators or pool aggregators on top of them. If I were to fuzz or to build a fuzzing suite for one of these projects, I will, what do you think I will do? I will mock this, or like the underlying pool, or actually do a whole deployment of the protocol on the at the underlying pool level, simulate everything. So you basically the aggregator protocol, the fuzzing suite, it's twice as big as like the normal protocol suite. I know it's counterintuitive, but it's the way you are able to find those rare rounding errors, edge cases, etc. And then about hardware and infra, you'll be wondering, or do you guys run this? How can I run it? How can I start, maybe? Or many other protocols like asking, even clients of us, customers of us ask us, where should we run this? I don't want to burn my computer, etc. So what we say is that is like a nice meme now. Our plans are measured in centuries, because we run I don't know, it's like 3 billion runs here. The average is like 80K, so you know the infra is good. So yeah, the tools basically require a lot of CPU, a lot of RAM, and if you want to do this at scale or in an auditing company for like many customers, or actually be able to iterate fast, because testing is about iterating fast, being able to solve everything quickly and not wait for the tool to run or something like that. You need like a good orchestration, job orchestrator, some kind of system for that. So yeah, we are planning to release distributed fuzzing. Really soon release like a job orchestrator for all the works for the customers, and maybe we release the CLI open source. I'm not sure, can't give details, but yeah, basically people were having slow local runs because Akina can't. I mean, it can run on a Mac M2 or something like that, or a Mac M4, but it's not gonna be like 3 billion calls. It's gonna be like 1 million calls at the end of the day, so makes no sense. Then fried CPUs, I've like meet people running our suites that actually like either the computer burnt or something like that, because it's just at 100, like I don't know, 100 and something degrees all the time, and then just syncing to a AWS server, to some kind of SSH setup is just pain, because everything is like super low level in some way, like interacting with the UX is not good, so we are just making this UX and orchestration layer on top of it, and also making it be distributed, so nodes can talk with them, and actually you can scale horizontally the infrastructure, basically. I think that's everything regarding the talk.
Yes, thank you very much, Victor. A round of applause for him, please, guys. Are there any questions? No? No questions?
I have a question.
All right.
Is more CPUs or higher clock speed more important?
It's multi-threaded, super multi-threaded. You can select, mostly in the tools, you can select the number of runners or workers. So the more CPUs, the better, basically.
All right. Thank you very much. Now moving on.